Hello, everyone. Welcome to another Friday of Happy Math Hour. So we are going to basically review for the final exam. So at any time, if you have any questions, to raise your hand and let us know. And so let's go ahead and get started. Okay. So we're going to start with the earlier chapters, and then we're going to make our way to the last chapters that we've covered. And so for this example, it says find any intercepts and test for symmetry to both axes and the origin. So to find the x-intercept, one of the things that we want to do is we can let y equal 0 and then solve for x. And so if we let y equal 0, then we're going to end up with 0 equals negative 2x plus 1. We're going to add 1 on both sides or subtract 1 on both sides, and then we can divide by negative 2. And once we simplify, then we end up with x equals a half. So our x-intercept is going to be a half and 0. And then for the y-intercept, we're going to let x equal 0. So anywhere you see an x, we're going to replace it with the 0. And then we simplify, so we end up with y equals 1. And so then this would be our y-intercept. For the axis of symmetry, if you were to graph it, then you could see that there is actually no symmetry. But we do have some tests that you. So if you want to check for axis of the x-axis symmetry, then we're going to take our original point and we're going to change the value of y. So we're going to make that y negative. So anywhere that I see a y, I'm going to replace it with a negative y. And then I'm going to go ahead and solve for y. So it seems kind of weird to replace it with a negative and then solve for it again. But as you can see here, if we did that, we divide by negative 1 and we end up with y is equal to a negative 2 divided by negative 1 is a positive 2x, and 1 divided by negative 1 is a negative 1. So if you compare this equation, y equals 2x minus 1, to the original, y equals negative 2x plus 1, we can see that they're not the same. If they're not the same, then we say that there's no x-axis symmetry. If they were to be the same, then we would say that it had symmetry. So for the y-axis, we're going to do something similar. We replace the x with a negative x. So anywhere you see an x, you're going to replace it with a negative x. So we end up with y equals negative 2 times negative x plus 1. We simplify. 2 times negative x is going to be a positive 2x plus 1. So when we compare the equation with the original, we can see that it's not the same, so it has no y-axis symmetry. And then the last thing for the origin is we change the x and the y to negative. And so anywhere you see a y and an x, we're going to add the negative symbols there. So we have a negative y is equal to negative 2 times negative x plus 1. If we simplify, then we end up with y is equal to negative 2x minus 1, which is not the same as the original function. So it has no symmetry on the origin. Okay, so our answer here would be no symmetry. Again, if you know what the graph looks like, then you can look at the graph and try to look for that symmetry. So write the standard form of the equation of the circle with the given characteristics. They give you the center and the radius. So the best thing to do is write the formula down for the standard form of a circle, which is x minus h squared plus y minus k squared equals r squared. In our center, remember that the first number is h and the second number is k, and then we have our radius. Okay, so we're going to substitute those values inside, so we get x minus negative 4 squared plus y minus 2 squared is 2 squared. So we can simplify, and we end up with x plus 4 squared plus y minus 2 squared is equal to 4. So this would be our standard form of the circle. Any questions on that one? Okay, another type of question is writing equations of a line given a point, and then they're going to ask us for a line that's parallel and a line that's perpendicular. So this is our equation, and this is the point that they give us. So the first step is to find the slope of this line here. So we're going to solve for y. And so I kind of just put all the steps here. So we're going to solve for y by subtracting 8x on both sides. And then we're going to go ahead and divide by -2. So we end up with 3 divided by -2 minus 8 divided by -2. And we end up with -3/2 plus 8 over 2. 8 divided by 2 is 4. So the thing that we're interested here is only the slope. So the slope, remember, is the value in front of x. And so we're going to end up with 4 as our slope. So I have it over here in red, m is equal to 4. So once we have our slope, we can just ignore everything else. And we're going to use our slope and our point. So for my point, I'm going to call it x1, y1. And then we have our equation here. So if we substitute those values, then we end up with y minus y1, which is 1. Our slope m, which is 4. X minus x1, which is 8. And then we're going to distribute the 4 into the parentheses. So when we do that, we end up with y minus 1 is equal to 4x minus 32. If I add 1 on both sides, then we can simplify. And we end up with y is equal to 4x minus 31. So if I was to draw this red line here with the original equation, then the lines would be parallel to each other. Now for perpendicular, we don't use m equals 4. We want to use the negative reciprocal. So we're going to use -1/4 instead of the m equals 4. We still use the same point and we follow the same procedure. So we end up with y minus 1 is equal to -1/4 x minus 8. Distribute the -1/4. So we end up with y minus 1 is equal to -1/4 x minus 8 times -1/4. -8 times -1/4 is going to be positive 2. Okay, so we add 1 on both sides, then we end up with -1/4 x plus 3. So if I graph the original equation with this one, the lines will intersect at 90-degree angles. And so that's what we say that they're perpendicular to each other. Okay, so the idea of writing an equation of a line is that you need to have at least one point and you need to know the slope. Okay, so let's go to another example. Find the following. So they give us f of x is equal to 9x plus 1 and g of x is equal to x squared minus 4. And they want us to add both of these equations. So f plus g of x is defined as f of x plus g of x. So f of x is what I have in red, 9x plus 1. And g of x is what I have in blue, x squared minus 4. So now we can combine like terms. So we end up with x squared plus 9x. 1 plus -4 is a -3. If we want to subtract, then f minus g of x is defined as f of x minus g of x. So f of x is 9x plus 1 minus g of x is x squared minus 4. Distribute the negative, so negative times x squared is -x squared, and negative times negative is a positive 4. Combine your like terms, so we end up with -x squared plus a 9x. 1 plus 4 is 5. And we can also multiply, so f times g of x is defined as f of x times g of x. So we have 9x plus 1 times x squared minus 4. So we're going to multiply these two parentheses. So we get 9x times x squared is 9x cubed. 9x times -4 is -36x. 1 times x squared is x squared. And 1 times -4 is -4. Combine your like terms. So we end up with 9x cubed plus x squared minus 36x minus 4. And then the last operation is to divide. So f divided by g of x is the same as rewriting it as f of x divided by g of x. So my numerator is 9x plus 1 for f of x, and g of x is x squared minus 4. There's nothing I can do here to simplify. So this is already simplified. And then that would be our answer. So one of the last things that we have to do is to find the domain. So we'll find the domain of the letter D here. And so we're going to end up with, to find the domain, we take the denominator, and we end up with x squared minus 4 is equal to 0. Add 4 on both sides, take the square root, and we end up with x equals plus or minus 2. So the domain can be any real number except for 2 and negative 2. The way we would write this is we would say negative infinity to negative 2, union negative 2 to 2, and then union 2 to infinity. So this is the domain. This is all the numbers that we can use except for positive 2 and negative 2. Okay, so our next example is using determining if something has an inverse. And so remember, to determine if something is a function, we use a vertical line test. To determine if it has an inverse, we use a horizontal line test. So in this example, you can see that if we draw this horizontal line across the graph, it's only going to touch in one place. And so we say that it's going to have a inverse. Okay, so here it says determine whether the function has an inverse. If it does, then find the inverse. So first we need to see if this is number 1. Is this even a function? So that's the first thing, is it has to be a function. And this is the square root of x minus 8. So we know that the square root is going to shoot up. So it looks something like this. Let me just draw it. This is the parent function, and it looks like this. So it would pass the vertical line test, therefore it's a function. It's going to also pass the horizontal line test, so it's going to have an inverse. So we can find the inverse. And so the way we find the inverse is by following this method. So first we're going to replace f of x with y. So this f of x is going to be a y is equal to x minus 8. Then we're going to switch the x's with the y. So remember, f of x was a y, so if I switch it to an x, now I get x. And then wherever I have my x, I'm going to have a y. And then you want to solve for y. So in order to solve for y here, I'm going to square both sides. And so on the left side, I get x squared. And then the square and the square root are going to become a 1, or people like to say they cancel. But in reality, it becomes a 1. So we end up with y minus 8. And then I'm going to add 8 on both sides. So I get y is equal to x squared plus 8. And so that's going to be our inverse. And so f inverse of x is equal to x squared plus 8. And so, you might be thinking, well, my result here, I know looks like this, right? That's a parabola, and it was shifted up. And so you might say, Mr. Trika, but the horizontal line test fails on this example. But remember that in the problem it says to consider x greater than or equal to 8. So they're only going to be looking at part of the parabola that is on this side. Let me just circle it. They're only going to be looking at going from 8 and beyond. So we're never going to care about this side. And so it's going to be okay. It's going to still pass the test. Okay. So to find the inverse, you're going to replace x and y and then solve for y again. Okay, so now these examples are from chapter 2. Sketch the graph of the function, apply the leading coefficient test, find the real zeros, and then plot it and do all this stuff, right? So we're going to answer A, B, and C here. So we'll do one at a time. So apply the leading coefficient test. So just as a reminder, if you forget all the rules, if you have these 4 graphs below, you can always remember the rules. So if you have an even exponent, then the graph is going to increase to the left and increase to the right if you have a positive leading coefficient. But if you have a negative leading coefficient, then it's going to fall to the right and it's going to fall to the left. If you have an odd exponent, then the behavior is going to be, if you have a positive coefficient, it's going to rise to the right and then it's going to fall to the left. And if it's a negative leading coefficient, it's going to rise to the left and fall to the right. So if we look at our example, we have an even degree. So it's going to either be the behavior like this one or this one. And then it has a negative leading coefficient. So now we're looking at this behavior here. Okay, so we can say that our graph is going to fall right and it's going to fall left. So that would be the last one, the last choice here. Okay, so we're going to use that in a little bit when we graph. So then we want to find the zeros. So remember, to find the zeros, that's the same as finding the x-intercepts. So we're going to let y equals 0. And so if g of x is equal to 0, then we solve for x. Notice that this is quadratic. So the first thing I want to do is, well, maybe it factors. In this case, it does. So we get x minus 8 times x minus 4. If it didn't factor, then you can use the quadratic formula, or you can use, if it was the way it's written, if it lends itself to use the square root property, then you could. It just depends on what method you prefer and which one you can use. So here it factors. So I'm going to set each factor equal to 0 and solve for x. So x is equal to 8 and x is equal to 4. So these are my zeros. And we also need to know if it's going to touch or cross. And so for each of those points, it's going to cross because they're not repeated. They're repeated an odd number of times. The y-intercept, you let x equal 0. So if you plug in 0 and 0 here, you end up with y equals negative 32. Then we want to find the vertex. This is the formula for the vertex. And so b is 12 and a is negative 1. So we end up with 12 divided by negative 2, and we end up with a positive 6. So if we plug this in to our equation, we can get the y value. So we end up with 4. So this is our vertex. So we're going to take all of that information and we're going to make our graph. Okay, so here's my my zeros, and then here's my vertex, and then I know that the graph falls right and it falls left. Okay, so let's try the next one. It's similar to the one before. Find the rational zeros, but this is a cubic function. So you can try to factor by grouping. That would be one way to do it. And then another way is to use the rational zero test, where you take the constant, which is 9, find the factors, which are 1, 3, and 9, and then the factors of the leading coefficient is 1. And so if we divide these, we get 1 divided by 1 is 1, 3 divided by 1 is 3, and 9 divided by 1 is 9. And so in the web assign, you would enter your zeros as negative 9, negative 3, negative 1, 1, 3, and 9. And these are possible zeros. So your next step to finding the real zeros is to take one of these numbers, and you can use synthetic division. We're going to take 1 and see if it works. In other words, what I mean by works is that your remainder would be a 0. So we bring down the 1. 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. 9 plus 2 is negative 7. Times 1 is negative 7. And then so we had a negative 9 minus 7 would be a negative 16. And that's okay. It's not a 0. So that means that 1 does not work. So we go to the next, try another number. So 1 times 1, we bring down the 1. That's the same one. So let me go here. So let's try negative 1. So we bring down the 1. 1 minus 1 is 0. Times 0 is 0. So we end up with negative 9. Times 1 is a positive 9. But we know that this 9 should be a what? Negative, because I copied it wrong. So this is a negative 9. So when you put the 9, and this was a negative, negative 9 plus 9 is 0. So that means that negative 1 is going to be one of our zeros. Now the great thing about this is that if we get our quotient, you can see that our quotient is now going to be quadratic. So we have x squared minus 9. We can set that equal to 0 and solve for x. So if I add 9 on both sides, I get x squared is equal to 9. So my solution here would be x is equal to plus or minus 3. So my zeros are -1, -3, and +3. Okay. And my factors, if I put everything on the same side, if I add 1 on this side and on this side, I get x plus 1 is my factor, x plus 3, and x minus 3. If we wanted to graph it, we plot our zeros. So we have the -1, the +3, and the -3. And then the behavior, notice that this is cubed and this is a positive. So our behavior is going to, that would be our next step, is going to rise to the right and it's going to fall to the left. And at the zeros, it's going to cross, okay, because the zeros were not repeated. And then we can plot some more points, right? We can, for example, if we let x equals -2 and we plot it, then we get y is equal to 5 and so on. So if we plot these numbers, and it didn't finish, but we can plot these rest of the numbers. So your graph is going to look something like this. It's going to come down here and then it's going to connect. So you can also pick the y-intercept, which would be at -9 down here. So this graph will come up and then it's going to go down all the way to -9 and then it's going to turn back around. Okay. So any questions on that? All right, so let's go to the next example. So here they give you a polynomial and they tell you that 4 plus 2i is 0. Since this is an imaginary solution, we also know that 4 minus 2i is also 0. So we want to find all the zeros. So we can use synthetic division. So I'm going to have 1, -12, 52, and -80. So I'm going to bring down the 1. And then 4 plus 2i times 1 is going to be 4 plus 2i. -12 plus 4 is -8. And then 2i is 2i. Then I need to multiply -8 plus 2i times 4 plus 2i. So we get 4 times -8 is -32. 4 times 2i is 8i. 2i times -8 is -16i. And 2i times 2i is 4i squared. So if we simplify this, we know that I squared is the same as a -1. Okay, so let me go back. So this would be a -1 times 4 is -4, plus a -32 is -36, and 8i minus 16i is -8i. Okay. So we end up with -36 minus 8i. If we add the 52 plus -36, I get a 16 minus 8i, and then I have to multiply this again times this, and if I do that, then I end up with all of this. Notice that my 32i and my -32i will become a 0. I squared is a -1 times a 16. -16 is +16, plus 64 is going to be 80. Then we end up with our 0. Okay. If you don't get a 0 here, then you know you did something wrong because they told us that this is a 0. So if we get the quotient, we get x squared. Remember, it's always one less. So if we started with x cubed, then we start with x squared plus -8 plus 5x plus 16 minus 8i. So we can do synthetic division again, but this time I'm going to use 4 minus 2i. Why? Because I know that the conjugate is also a 0. So my coefficients are 1, -8 plus 2i, and 16 minus 8i. Bring down the 1. Multiply 4 times 1 is 4. -2i times 1 is -2i. -8 times 4 is -4. 2i plus -2i is 0. And then we're going to multiply 4 times -4 is -16. and negative 2i times negative 4 is positive 8i. Okay, so if we add them, we get 0. So now, since this was x squared, 1 less is x. So this would be x minus 4. Can set that equal to 0. And so x is equal to 4. So your zeros are x equals, there should be a 4 right here. Okay. And then x equals 4 plus 2i. And x equals 4 minus 2i. So this 0 should be x equals 4. Okay, so that was finding the zeros. Now we're going to look at the rational functions here. So we have this function 1 divided by x plus 3. You want to find the domain. So remember, to find the domain, you look at the denominator. So for the denominator, we said x plus 3 equal to 0. And so we end up with x equals negative 3. So your domain is going to be all real numbers except for negative 3. And so here our answer would be letter D. Okay. So this would be our answer. So now for letter B, identify the intercepts. So for the x-intercept, we're going to set y equal to 0 and solve for x. So if y is equal to 0, we get 0 is equal to 1 divided by x plus 3, multiplied by x plus 3 all the way across. So multiply this times this. So 0 times x plus 3 is 0. X plus 3 times x plus 3 is going to be, they're going to cancel each other. So we get 0 is equal to 1, which is not true. So we say that there's no x-intercept. Now for the y-intercept, we let x equal 0. So if I let x equal 0 here and x equals 0 here, then I end up with 1/3. So that's my y-intercept here. So vertical asymptotes and horizontal asymptotes. Just a review really quick. The vertical asymptote is represented with a dotted line vertically. And we can find it by factoring the numerator and denominator completely and canceling any like factors, and then setting the denominator equal to 0. If you happen to cancel a like factor, then we end up with a hole in the graph. Okay. So if we factor both numerators, these are already factored. So if we set the denominator equal to 0, we end up with x plus 3 equal to 0. Subtract. So we end up with x equals negative 3. It's going to be our vertical asymptote. Let's check for a horizontal asymptote. So if we were to graph it for the vertical one, it would look like this picture here. So the horizontal is going to be represented with a horizontal line. And there's 3 different possibilities. So the first one is if your numerator for their degree is less than the degree of the denominator, then we're going to end up with a horizontal asymptote of y equals 0. And if the degree of the numerator is the same, we can take the leading coefficient of the numerator and the one for the denominator. And if the degree is greater than the denominator, then there's no horizontal asymptote. So here we have the degree of the numerator is 0 and the degree of the denominator is 1. So this is our situation. So that means that our horizontal asymptote would be at y equals 0. So these are our asymptotes. So let's go ahead and we have all of our information. We have our intercepts, vertical asymptote, horizontal asymptote, but we need some more points so that we can get a better idea of what our graph is going to be. So let's plot our graphs. And so here in the green point here, this is going to be our y-intercept. And then additional points, I recommend that you graph some on the right side of the asymptote and some on the left side. Okay, so I'm going to pick a -2, and if I plug in -2 for my x's, I end up with a 1, and if I plug in a 2, this one here, I end up with a 1/5. Okay, and then I'm going to plot some more points. -4 is on the left side of the asymptote, and so if we plug that in, we end up with -1, and -5, if we plug it in, we end up with a -1/2. And so here are the points, right? So this was for f of -2, and this is for f of +2, -4, and -5. So it looks like a whole bunch of points everywhere scattered, but we do understand what the vertical asymptotes are for and their behavior. Then we can sketch our graph based on that. Remember that we have an asymptote right here at y equals 0 that we just don't graph it because that's the y-axis. So we know that our graph is going to get closer and closer to the asymptotes, but it's never going to touch, and the same on the left side. Okay, so that is using the rational functions. And then I think Mr. Carizales is going to um, go ahead and take over. So this is just a picture from WebAssign, and so he'll start with the next problem.
All right, thank you, Ms. Chuka. Awesome. All right, so let's look at this example. Use the properties of logarithms to expand the expression as a sum, difference, and/or constant multiples of logarithms. So the only way we can do this for the expansion is if we have a common log. So, and that's what we have in this particular problem. We have a log of base 5. And what we see inside this log is we have, the first thing we see is we see a division going on. We have the square root of x squared minus 9 being divided by 4. So what we can do is we can apply what's called our quotient rule. And our quotient rule is going to say that when I have a log of the same base, I can expand it into a subtraction. So this is going to give me the log of base 5 of the square root of x squared minus 9 minus the log of base 5 to the 4. So um, we can also continue simplifying this. If we see here, we can rewrite the square root as an exponent. And we know that the square root written as an exponent is to the 1/2. So we'll go ahead and do that. So we have the log of base 5 of x squared minus 9 to the 1/2 power minus log of base 5 to the 4. So what we can do now is we can apply our power rule. So our power rule says that if we have an exponent to a given log, we can multiply that exponent to the log. So, or bring it to the front, right? So then we will have 1/2 log of base 5 of x squared minus 9. But we're still not done. We can see that we can rewrite this input here, or this x squared minus 9 that's inside this log. We can see that this is can be written as a difference of squares, or we can factor it, right? So x squared minus 9 can be written as x minus 3 times x plus 3. So now what we see here is we have a product of two things for a given log. So now we can use our what's called our product rule. And our product rule says that when we have two items that are being multiplied to a same logarithm, we can add two individual logs. So what we're going to result, our final answer is going to be 1/2 log of base 5 of x minus 3 plus 1/2 the log of base 5 of x plus 3 minus the log of base 5 of 4. And what we did is we took one log and we expanded it to three different logs. Okay, so this is what's called expansion. So let's look at these more examples here. So let's look at the opposite now. So instead of expanding, what we want to do is condense. And we're going to use our same properties to be able to do that. And what they want us to do is they want us to convert multiple logs into one single log. So let's start with A. Okay, so A, we have log of just to review, when we don't have a number for the base of the log, we automatically know that this is a base 10. Okay, so we are dealing with the same log throughout. These are all base 10 logs. And what we can do is we can just start from left to right. Okay, excuse me. So we see that we have numbers that are in front of our logs. So what we can do is those are represented as exponents or using the power rule, right? So we have log of base 10 of x minus log of base 10 of y to the 6th power plus log of base 10 of z to the 7th power. All right, so now what we can do is we can again continue condensing, and we can combine the left with the right. So the first one, we have the log of base x minus the log of base 10 of y to the 6. We know that we can use our quotient rule to do this, and we're going to have the log of base 10 of x divided by the y to the 6th power. So now we're left with an addition, and again, that's also the product rule. So we're going to multiply the two inputs of the logs together, and this is going to give us the log of x over y to the 6 times z to the 7. Yeah, I like to simplify it. I don't know if we simplified it. Yes. So when we multiply this, we like to have this as one input, the log of base 10 of x to the z to the 7th divided by y to the 6th. Okay. All right, let's look at B. Um, for B is using the natural logs, but they work the same way. Okay, um, so what we're going to do is, on this particular one, let's see here. Um, oops, I'm condensing, and they want us to. This one is condensing. So I'm flipping over. Actually, I'm switching problems now. So what we're going to do on these is we're going to solve logs. Okay. Um, So let's go ahead and solve this A. They want us to solve natural log of x minus natural log of x plus 6 is equal to 7. So they want us to solve for x. So let's go ahead and apply some of our properties in order for us to do that. So what we're going to do is we want to combine the left side in order for us to start eliminating some of these variables, right? Or if we can eliminate some of the variables. So I see that natural log of x minus the natural log of x plus 6, these are the same logs, so I can condense it by using my quotient property, and that's the division, right? That's the natural log of x over x plus 6 is equal to 7. Okay, so now what we can do is to solve, we can convert it. We can convert this log into an exponential form. I think that's the easiest route to work some of these problems out. So let's go ahead and do this. So to convert this, okay, yeah, we can use the log, or we can use the um, the natural log, or we can use the log of a base, right, to do this. And let's use the log of a base in order so you can see the the inverse of each other, right? The opposite. We're going from a log to an exponent because these are inverses of each other. So if I have the log of base e, okay, which is the same thing as the natural log of x over x plus 6 equals 7. So the base is e, so my exponent is e. The output of the log becomes the input of the exponent. So this is e to the 7. The input of the log becomes the output of the exponent. So this is x over x plus 6. So now we can see that if we wanted to solve for x, we first have to multiply both sides by x plus 6. Okay. We want to go ahead and distribute the e to the 7. And then what we want to do is we want to combine the x's together so we can factor it out. So I'm going to move the x to the left side, and I'm going to move e to the 7 times 6 to the right side. Now, again, this is a number, but I don't want to calculate it because I don't want to be working with long numbers because these numbers probably don't terminate. So I'll just do my simplification with my calculator at the end. So again, I move my x to the left by subtracting x on both sides. I move e to the 7 times 6 to the right by subtracting e to the 7 times 6 on both sides. And then again, let's go ahead and factor the x on the left side. So when I do that, I can factor the x, and it's going to give me x times e to the 7th minus 1 is equal to minus e to the 7 times 6. To solve for x, I'm going to divide both sides by e to the 7 minus 1. Okay, and when I do this, I get this value. x is equal to negative e to the 7 times 6 divided by e to the 7th minus 1. And again, when I plug this into my calculator, I'm going to get a very long number, but they probably ask us to round, or the problem did say to round to 3 decimal places. So that's where I get minus 6.005. Okay, so just be careful on that rounding. You always want to look at the number after the decimal place that they want us to round. If that number is bigger than 5, we move that third number up one. If that number is less than 5, we leave it alone. Okay? All right, let's go ahead and do, of course, if you have time, you always want to check your solutions. Okay? All right, so let's go ahead and do B. The natural log of x plus 9 is equal to the natural log of x minus 6 minus the natural log of x plus 6. Again, let's use some of our properties to condense to try to solve for x. Okay, so we can see that on the right side, we can condense it. We have a subtraction of two equal logs. So we'll use our quotient property. So it's going to give us the natural log of x minus 6 over x plus 6. And now what we can do is we can use our one-to-one property. When we have two logs that are equal to each other, the only way that these two logs can be equal to each other if their inputs are equal. So we'll use our one-to-one property to set the inputs equal to each other. So x plus 9 is equal to x minus 6 over x plus 6. Let's go ahead and do the same thing that we did before, do a little algebra to combine the x's. So we'll first multiply the x plus 6 on both sides. Go ahead and distribute. And we will simplify, right? So we see that we're going to have a quadratic. So what we'll do is we'll just move everything to one side. And since there's more terms on the left, let's move everything to the left. So let's move this x minus 6 to the left by subtracting x and adding 6 on both sides. Okay, so we're going to get this number after we combine our like terms. We're going to get x squared plus 14x plus 60. Now, so there's several ways to solving for x. We can use our quadratic equation, or we can try to factor this problem out. So for practice purposes, let's go ahead and use our quadratic equation. And when we do that, we see that we were going to get a negative number inside the radical. So that means we were going to get an imaginary number. So that means there's no solution for this problem. Okay. All right. Any questions so far? All right. Let's move forward. Let's go ahead. All right, Samantha. Great. Thank you. So let's look at this other example. Solve the logarithmic equation algebraically and approximate the result to 3 decimal places. So again, we're going to do the same thing as before. We see that on the left side, we have a subtraction of two equal logs. They're both logs of base 9. So we can use, again, our quotient property. This is going to give me the log of base 9 of x over x minus 8 is equal to 1/2. Let's go ahead and convert it to an exponential form. So this is going to give me the base of the log is also the base of the exponent. The output of the log is the input of the exponent. The input of the log is the output of the exponent. So we know that 9 to the 1/2 is just the square root of 9 equals to x over x minus 8. Let's go ahead and simplify by multiplying x minus 8 on both sides. And we're going to have two different answers, right? We're going to have from the square root of 9, we have a plus 3 and a minus 3. So when we solve for this, we get a x value of 12 for one, and we get an x value of 6 for the other. So what we want to do is we want to test these answers to see if these are either both of them are a solution or only one of them, right? So when we check x equals 12, okay, we see that it's a positive solution, so it is a solution. But if we see that when we plug in x equals 6, we get a negative number here. 6 minus 8 is equal to negative 2, and we cannot input a negative value into a log, so hence x equals 6 is not a solution. So our only solution was one of them, which was x equals 12. Okay. Oh wow, I think I went through those too quickly because we're at the end. Any questions? Is there anything that you would like us to go over in the next 15 minutes that you have concerns about coming up with your finals? So finals is this coming week. Um, Awesome. No questions? Oh, you're very welcome. Ms. Chuka, would you like to add anything?
Just wanna wish you guys a great final exam, and then hopefully one day we'll meet. Maybe some my office is in the A building at Valle Verde. If you ever need anything, you can stop there. 2506.
Well, and my office is in Rio Grande, so if anybody needs anything, again, I'm off in Rio Grande, and my office is in the Emporium building, in the M building, and it's E114. Okay, so again, we hope to see you all one of these days. Good luck with your finals again. Thank you, Ms. Chuka. I know you guys are all gonna do great. Just study hard, just review, 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 and you guys will do awesome. Well, happy finals. Good luck, everyone.
Thank you, Ms. Chuka. Thank you, Mr. Carizales, for your presentation. We do want to remind you guys about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and the other short survey to receive credit for attending. The code word is final and the link has just been posted. Thank you all for coming in today. We hope you have a lovely weekend. Good luck on finals. If you guys have any questions or any concerns, we also have online tutoring opened until 11 p.m. tonight. Good luck on finals. And if you guys need anything, please let us know. Thank you.